Hi everyone, this video is going to be a review of the topic of calculating DeltaH from tabulated values. When we say tabulated values, we usually are referring to possibly either the DeltaHac or the DeltaHf. So if you see those symbols or they're given to you, it's probably, or you're referred to a table, it's probably a cue to use those values to do this calculation. This is a more exact calculation than the way that we learned to estimate earlier in the course using bond energies, and it's a little less cumbersome than using Hess's law because you don't have to have every reaction to add up to everything. You're given these values and you kind of just plug them in. Most students prefer this because it's a little more plug and chug, it's a little more straightforward. However, it's important that you understand what you're doing and not just how to do it. So we're going to do a little bit of that. The first thing I just want to mention is that you'll see these equations a lot, and it's important that you know what they are. So this first one, of course, the DeltaH naught is our old friend, the change in enthalpy, right? So this is just the change in enthalpy in any reaction. And that's the nice thing about this is we really can use it for any reaction as long as we have the values for it. So then you're going to see this symbol a lot. This is a sigma. This is an uppercase Greek sigma. What it means is sum or total. All right, so anytime you see that sigma, it's going to mean you're going to add up all the things that come after that. And what comes after that is this, is n referring to the stoichiometric coefficient, not the actual number of moles, which is an annoyance of mine. And so sometimes when I write this equation, I don't write the n because it confuses people. In this case, the n is referring to the stoichiometric coefficient. A lot of textbooks write it this way, so I wanted to bring it up. The DeltaHac here, it's going to always be products minus reactants, right? The DeltaHac values are values that you're going to find in a table. The AC here stands for atom combination, or sometimes people will say atomic combination, but it's the atom combination. In other words, you're going to combine the atoms together, see how much energy that is. You're going to write that number in a table, be able to use it in this equation. Down here, this is the same equation down here, except that we're using these DeltaHf values. The F is for formation. Formation is a little more complicated what that means. I'm going to go over it here in a second. Right? It's not just formation. It's formation under certain conditions, blah, blah, blah. Okay, I am a big proponent of DeltaHac values. A lot of textbooks only talk about DeltaHf, and I think that's dumb, but that's just my opinion. So you use whatever you have available to you, but the reason I like the DeltaHac values, again, the AC stands for atom combination. The reason I like them is because they actually correspond to something real. So if you look at, so for example, I've got here N2, you take a nitrogen atom in the gas phase, a nitrogen atom in the gas phase, and you combine them. In other words, you combine the atoms, get it? AC, atom combination. You combine those together and you get the molecule N2. And that has a this reaction, you can measure the DeltaH for this. And the DeltaH for this reaction is negative 945. That number should ring a bell because earlier in the semester we did several examples with nitrogen, and the bond energy for the nitrogen triple bond is 945 kilojoules per mole. Okay, so in other words, the DeltaH, this is specifically a DeltaHac because it's the atom combination. This DeltaH of atom combination is the total of the bond energy in that molecule. It's easier to see that in some of these smaller molecules. Another one you'll see is like oxygen gas plus oxygen gas yields O2 gas. And the DeltaH for this reaction, which happens to be the DeltaHac, is going to be negative 498 kilojoules per mole, and that's the bond energy of the O to O double bond. All right. So one subtle difference here: the ACs, because you're forming bonds, these are always negative, and the bond energies are always positive because it's how much it takes to break it. So they're sort of the same number but opposite in sign. But you know from earlier discussions that anytime you are taking atoms and forming bonds only, there's no bonds being broken here, you're going to have a negative DeltaH. Okay, so all of the DeltaHac values you're going to come across are all negative because they're all forming all of the bonds. It's like the total bond energy in the reaction. The DeltaHf values, now we call this DeltaH a formation. It is the formation of a substance, compound, molecule, from its elements as those elements exist at room temperature and pressure, okay? So room temperature, meaning 25 Celsius, and room pressure or normal pressure, meaning 1 atmosphere, typical atmospheric pressure at sea level. So you have to, the problem with this that I think is that you have to know, to actually understand it, you have to know what the, how the elements exist at room temperature and pressure, and some of them are fairly obvious, like O2. So for example, O2 is how oxygen exists at room temperature and pressure, H2 is how hydrogen exists. But, you know, there's like 4 different forms of like sulfur and phosphorus, and you have to know which one it is that refers to. The problem is here that you don't really have to know most of the time. Most of the time you can get away with plugging and chugging, but I think it's kind of silly that we rely on these numbers that we don't really understand where they come from. Anyway, that's my beef with DeltaHfs. There's also this funny thing where the DeltaHf of an element as it exists at room temperature is 0. So the DeltaHf of O2 is just 0. And the same for the DeltaHf of solid iron and the DeltaHf of H2. And so it is, like I said, it's a pet peeve. But some people like them, I think, because a lot of them come out to be 0. But at the same time, it's kind of a meaningless number because it's referring to its energy difference from the elements, and are the elements more stable, blah, blah, blah. And sometimes they're positive, sometimes they're negative. I don't like them, I try to avoid them, but you need to know what they are because lots of other people use them. So this reaction I've given you here where we're taking hydrogen and combining it with oxygen, 1 mole of hydrogen, half a mole of oxygen, getting 1 mole of H2 gas. This is the DeltaHf for H2O gas, okay? So if you go to a table and look up H2O gas and DeltaHf, you're gonna find this number here because that's the DeltaH that corresponds to this reaction where you're forming the water from its elements as they exist at room temperature and pressure. Okay, now meat and potatoes of this is that most of the time you're just going to be plugging and chugging. So here I've given a practice problem that I'm going to work through for you where we're going to calculate the DeltaH for the reaction that's given below, this one here, and we're going to use these DeltaHac values that we were given in this chart over here, okay? All right, so we're going to set this up using the equation DeltaH is equal to the sum of DeltaHac of the products minus the DeltaHac of the reactants. Incidentally, this minus sign in this equation comes from Hess's law. You don't really have to know that, but I think it's interesting. So anyway, that's the origin of that minus sign. So what we're going to do is just plug everything in here. Okay, so our products are over here. So we've got 1 mole. And I always like to multiply the coefficient, even if it's 1, just to remind myself that I did it. So we're going to do 1 mole of CO2, which is 1608 kilojoules per mole, plus 2 times the water value, which is minus 926 kilojoules per mole. And then there's a minus sign here, and you got to be careful. This minus sign has to apply to all the reactants. So I always like to use brackets here and do 1 times negative 1662 plus oxygen, which we've got 2 of those, times 498, minus 498. Okay, so notice that that minus sign has to stay out in front of both of the reactants. So I'm going to add up the reactants first, and then I'm going to apply that minus sign, okay? So what do we got here? I'm going to simplify this down a little bit. So we've got minus 1608 and 2 times minus 926. So this first set of brackets here is negative 3460 minus, now the second set of brackets here is minus 1662 plus 2 times negative 498. So that gives me 2658. And again, I'm just being careful here, right, to not screw up the math. So I've got a negative and a negative, 2 negatives in a row like that, turn that into a positive. You really should think of this minus sign here as just flipping the sign and not as making it negative. That's really best for you to start getting used to. That negative signs mean flip the sign, they don't mean make it negative. Okay? All right, so I'm going to have, punching this through the calculator, that's going to give me negative 802 kilojoules per mole. Okay. The unit is kilojoules per mole because I was given the delta H ACs in kilojoules per mole. All right, so fairly straightforward, mostly just plugging and chugging. Be careful that you don't lose your minus signs along the way. Okay, all right. I have a practice problem set up for you here. This one's using DeltaHf values, formation from the elements as they exist at room temperature and pressure. So go ahead and pause the video, get out a piece of paper, get your calculator, get your pens and your pencils, do the problem, and then restart the video. Okay, here we go with the answers. So the delta H value here is going to be given by the equation delta HF of the products minus the delta HF of the reactants, right? So now we're going to plug in, and remember to use the stoichiometric coefficients, okay? So we've got, what do we have for products? We have 2 times water, which is negative 286, plus 1 times oxygen, but oxygen is 0. I just like to write it out to make sure that I got it, though. So, all right, minus reactants. We only have one reactant here, so that's fairly easy. 188. Just remember to multiply that 2, because you got a 2 out here, this 2 from the 2 for the water. Okay? All right, simplifying here, we've got, this is where that delta HF being 0 for oxygen is kind of handy. And again, I really think it's the only reason that people use these, because it makes occasionally you get a 0 somewhere. But I could be wrong. I know some people really like them. So, all right, and then 2 times 188, that's going to be negative 376. And then that's going to be negative 572 plus 376. So the delta H here is going to be minus 196 kilojoules per mole. All right, so for every mole of H2O2, or every 2 moles, because there's 2, we get we get 196 kilojoules of heat evolved. Notice that this is exothermic, right? So just reviewing that concept because the delta H is negative. And that's it. Okay, so it's mostly just plugging and chugging. It is helpful for you to know where the numbers, delta HAC, atom combination, and delta HF, formation from the elements as they exist at room temperature. I think it's good that you know where they come from, but as long as you can do the math part here at the bottom, this is going to cover like, 80%, 85% of what you need to do most of the time. All right, thanks for watching. I hope this was helpful. Leave me a comment, get in touch if you have any questions, and thanks for watching.